Okay, we're going to finish chapter 5.3. We did conditional probability situations. We're going to finish this chapter. The second objective is um, using the conditional probability rule to solve an AND situation. So one thing, there's not a lot of algebra in statistics. We did a little bit in Unit 4, and we're going to do a little bit here just to show you this formula here. The formula that we just had before was the probability of F given E is equal to the probability of E and F divided by the probability of times the probability of E. And so if you remember some algebra, we can rewrite this. This formula is a new formula here. If you can see that if I solve for this here just by cross multiplying, you end up with this formula here. You end up with the probability of E and F is equal to the probability of F, probability of E times the probability F given E. So this is the formula just comes from what we already know. It's just rewriting it. So we can use that to solve problems. The probability of a driver who's speeding gets pulled over is 0.8. The probability that a driver gets a ticket given that she or she was pulled over is 0.9. What is the probability that a random selected driver who's speeding gets pulled over and gets a ticket? So this is what we have. So the probability of a driver who's speeding gets pulled over, speeding and pulled over is equal to 0.8. The probability that a driver gets a ticket given that they're speeding, right? Given that she is, oh sorry, not speeding, gets a ticket given that they're pulled over is 0.9. So what we're really trying to find out, what is the probability that a randomly selected driver who is speeding gets pulled over? So we're really looking for speeding, pulled over, and gets a ticket. So you can see it's an AND situation that we're solving right here. It's an AND. And in order to answer that question, the answer, you just end up multiplying these two things together. So you end up having 0.8 times 0.9, and so that gives you 0.72. And so that's how you would solve that problem there. So it's just using the formula in a backwards way to get that. And then that leaves you with one more example here, kind of using that information there. Let's see what we got going on here. Take ahead and read the situation. Okay, as you finish reading this, you can recognize there's not a specific conditional probability, and this is a special situation of conditional probability where it's going to rely on this idea of back to this independence idea that we're going to talk about. So let's answer these questions. Suppose that we select 1 out of 10,000 African Americans. What is the probability that he or she has sickle cell anemia? Well, we have the numbers there. The probability that they have sickle cell anemia is just going to be 27 over 10,000, or 27 10,000s. And so that turns out to be 0.0, that's tens, hundreds, thousands, 27. If you're not sure, let's confirm that. The numbers are so small you get kind of mixed up. 27 divided by 10,000. And so it's 0.0. Oh, I have one extra zero, sorry. It's 0.0, tens, hundreds, thousands. Oh, yeah, 10,000s. There we go. 0.027. if two individuals from this group are selected, what is the probability they both have sickle cell? So it's kind of conditional. Probability that the first has sickle cell, right? Sorry, the probability that the second one has sickle cell, given that the first one has sickle cell. I could also see this as a sequence of events, technically. What's the probability? So you might be able to see it this way. The probability that the first has sickle cell and the second has sickle cell. So it gets a little tricky sometimes because I can see it two different ways. What's the probability that the second one has sickle cell given that the first one has it? Would be the same as what's the probability the first has sickle cell and the second? And so in this case, it's just going to be 27 over 10,000 for the first one times 26 over 999. Where do I get those numbers from? Because after the first person has sickle cell, the second, there's oh no, it's not 27. It's going to, not 26. It's going to be 27 over 9,999. It's because and again, let me fix this here because we're not assuming that these are dependent events. The first person out of the 27 has sickle cell, so it's 27 of 10,000. Now, after the first person we know has sickle cell, we then now there's only 26 people left out of the 9,999 of the 10,000, and so then that's our answer right there. It's going to be multiplication of those two, get your answer there. And now question C, which I'll do those after. Question C changes the scenario a little bit. Compute the probability that the two individuals from this group who have sickle cell anemia assuming independence. And what that means is do the same problem. The only difference is let's assume that there's independence. Here, these were dependent events. That's why we decreased when the first person had it, so we decreased. What they're saying is do the same exact thing, and the only difference this time is if you assume independence, that they're independent events, we just end up doing this multiplication, and that's it. And so the answers are going to be very close because these numbers are so small. These numbers are so big. The denominators are so big, and these are so small that the answers are going to be very similar. And so when you do those calculations, we're going to do the first one. And again, it's because of this independence. We're going to get, I need 27 times 26. And that's going to be divided by 10,000 times 99. Close that. And so then you end up with like this number that's 0.0000 0.0, that's 5 zeros and then a 7. And then if we do assuming independence, then this is the math we do there. And so then that just becomes, what do we want? 27 times 27 divided by, let's do that again, 27 times 27, and that's going to be divided by 10,000 squared. And so notice your answer is 0.0, that's 5.000007. So notice they're pretty much the same answer. So you don't have to, you can just assume, you don't have to do this weird calculation, which you do here by subtracting 1, because they are dependent events. But if we assume independence, we can just do it this way, and the answers are the same. So it doesn't matter. And here's the note: if small random samples are taken from large populations, it is reasonable to assume independence of events. So that's what we were doing up there. Okay, And then the last thing for this section, after you do that and practice some, the last thing is you'll get a few homework problems that ask you if two events are independent. And then so make a note of this here. Two events are independent if this is true or this. So you can test to actually do the calculation to see if they're independent. And you'll see a couple examples on homework, and then we'll do some in class on this. But I'm going to leave you to that. Just do these calculations to check for independence when you get to those problems.